Hi, my name is Michael Lavara, and welcome back to my series on paint and materials effects testing. This is part 7, where I take a look at Swift's 100R unleaded Avgas product. If you haven't watched my previous videos, I encourage you to take a look at the previous 6 as time allows. They may answer some of the questions that come up while watching this video. In fact, they've set the basis for the things that I'm testing today. I also want to make it abundantly clear. I have no allegiance to any fuel company, whether it be GAMI, Swift, VP Lyondell, or anything else in the oil and gas industry. I initiated this testing all on my own accord in December 2024, based on the issues that we're seeing at Reed Hillview Airport and local airports with the rollout of GAMI's G100UL. And I've personally financed this in both time and money. And I can tell you that I'd rather be flying one of these 2 airplanes behind me than spending my nights and weekends working on these videos. But I feel like this is my contribution to the GA community at this time. So, with that said, let's take a look at Swift's 100R product. So what's in this video? First, I'm going to cover some industry updates, which start with Eagle's presentation at EAA AirVenture, Santa Clara County's Airport Commission meeting where the Cessna 421 was mentioned in August, GAMI's materials testing summary report that was released a few weeks ago. The National Academy of Sciences has a preface on unleaded fuels that I think is a good read. And then we're going to dig into what you're all waiting for, a first look at Swift's 100R and my materials testing. At AirVenture 2025, several forums were held throughout the week which discussed unleaded fuels. The presentation I've linked here, and I'm going to show a slide from, is from the Eagle Initiative. This slide highlights some of the issues that I've brought up in previous videos. That is, the balance between octane and materials compatibility with the replacement of lead in our fuel as an octane enhancer. I'm a visual person, so I asked AI to generate my perspective of what's going on with the current unleaded fuel topic. That is, the higher octane fuels might possibly have materials compatibility issues, whereas fuels that are chosen to have less of a material compatibility situation have less octane and may not fit 100% of our fleet. So I guess what I'm saying is, there's no free lunch in life. After AirVenture, Eagle posted this update, which included audience member questions from AirVenture. I've linked it down below for reference. Back in June, I presented my observations to the Santa Clara County Airport Commission. In August, they had a follow-on meeting, and discussions centered from the Commission on the rollout of G100UL and the reports from users. Most notable from this was the mention of the Cessna 421 at Reed Hillview, where the owner stood up and spoke to the Commission, stating that based on the cost to return the 421 to service, the insurance company declared it a total loss, to the tune of nearly $600,000. You can hear the audio of the owner speaking linked below, and it's about the 1 hour and 1 minute mark. In addition, the previously reported Cirrus and Piper PA-32 have also had insurance claims paid that noted G100UL caused damage to their aircraft. Of note, the Reed Hillview Airport Director also shared at this meeting that he has had struggles with G100UL. While he continues to use it, he didn't elaborate on what those struggles were. Recently, GAMI released a summary of its materials testing, and I want to say this is a positive step to see open communication and transparency on materials testing. And while it's quoted as being a summary of their testing, the testing appears focused on component assemblies. There's no specific mention of easy turn lubricant, MIL 6000 hoses, fabric testing, or paint testing. Before I move on to the testing results of Swift's 100R, I want to point out that the National Academy of Science has a publication entitled Options for Reducing Lead Emissions from Piston Engine Aircraft. This was published in 2021 and is a consensus study regarding unleaded fuels and some challenges faced in previous fuel development efforts. I highly recommend reading this document. In the interest of time, I only want to highlight a few points. The document lays out the 4 general categories of octane enhancers, which we've discussed before as aromatics, oxygenates, aromatic amines, and metals. It points out that octane-enhancing additives provide some challenges, whether it's vapor pressure, hot and cold starting, material compatibility, storage, freeze point, or even toxicity. And what does this mean? The industry is going to have to weigh the pros and cons of fuel. Either we have fuels that meet the octane requirements and are highly aggressive towards materials, or we accept a slightly lesser detonation margin and perhaps roll back the performance of some engines by a little bit. I'll dig into this later, but I'm not quite sure yet what that trade-off will be in performance. And the book builds off this in a later section, noting that while the development of a drop-in unleaded fuel that can satisfy the entire piston engine fleet is a highly desirable goal, attainment of that goal is not assured, and a singular focus on achieving it risks the neglect of other opportunities to reduce lead emissions in the GA fleet. A few months ago, I mentioned in the closing statement in one of my videos that I wouldn't hesitate to give other unleaded fuels equal or more scrutiny than I have given to GAMI's G100 UL. In response to that, Swift Fuels offered me a sample of their 100R unleaded Avgas to test, and I finally received that sample back in August. I'll discuss some of the technical specs of the fuel as I know it, my visit with San Carlos Flight Center to learn about their experience, go over their ASTM production spec, ask some questions about octane, and then, for the majority of this, dig into materials testing that I've performed to date on Swift's 100R fuel. In regards for technical specifications for 100R, Swift has published very little about their fuel, and the website has a scant mention of 100R. The following information is what I have gleaned from public data. It's stated that Swift 100R is a 100 motor octane aviation gasoline designed to fully replace 100 low lead leaded avgas across the entire global piston fleet. It's mentioned be drop-in ready, and I'll caveat that with words on their website stating, without having to replace aircraft hardware prior to use. The fuel is currently only STC'd for Cessna 172R and S models, and an expanded AML is in progress for both aircraft and engines. It uses ETB as an octane enhancer, and there's been many questions on the internet fielded whether it can be used in California. And lastly, the fuel appears to weigh about 5.8 pounds per gallon, which is slightly lower than 100 low lead. Let's dig into the term drop-in. This has been a hot topic on the internet and from many users who've experienced adverse effects with other fuels. This really hinges around 2 points. Does the fuel's performance, i.e. octane, meet or exceed 100 low lead's properties? And does the fuel require any changes to the aircraft? Let's call it ignition timing or materials replacements. Let's look at what the FAA has published about the term drop-in on their unleaded fuel development facts and definitions. A drop-in fuel does not affect the airworthiness and performance of the existing fleet of aircraft and engines and typically does not require new aviation fuel-related operating limitations. An extensive qualification test program that encompasses both fuel property evaluation and engine and aircraft testing would be required to determine if a new fuel is a drop-in. The FAA defines airworthy, meaning that the aircraft conforms to its type design and is in a condition for safe operation. So what makes an aircraft unairworthy? Is it leaks, clogged injectors, any other fuel system issues? Several aircraft have had issues that required repairs after introduction of a new unleaded fuel. I would argue that they were not airworthy for a period of time while those repairs were performed. San Carlos Flight Center in San Carlos, California, started using 100R on a restricted basis in November 2024. In August, I took a short flight over to the airport to visit with them and learn more about their experience using the fuel over the past 10 months. During my visit, I met with Alessandro Franco, the owner of San Carlos Flight Center, and his head mechanic. In the past 10 months of operating their fleet of 172s on 100R, they've consumed over 35,000 gallons of the fuel, amassing over 5,500 TAC hours on the fleet of aircraft. And out of that 5,500 hours on their fleet, a single Cessna 172 has operated over 600 hours on 100R. In addition, they've noted no in-service difficulties while using the fuel. That means no leaks, paint staining, or other mechanical issues. Furthermore, they went on to describe how since switching from 100 low lead to unleaded avgas, they've noticed a serious reduction in wear metals on their aircraft. Shared with me here is a Blackstone oil report from one aircraft that was using 100 low lead up until late 2023, then switched to UL94. And it used UL94 with occasional 100 low lead fill-ups until introducing 100R in November 2024. I've highlighted some areas of interest in red, which includes the wear metals and a segment on calcium. Calcium, I believe, is what their anti-valve rescission additive is primarily made up, and it spiked up with the introduction of 100R. A second oil report sample was given to me for the aircraft that has the highest time on 100R, some 600 plus hours. It switched to 100R in November 2024, and since it had already been using UL94, the wear metals were already low, and have continued to stay low the entire time. And again, San Carlos Flight Centers reiterated that they've been pleased with the fuel's operation and have had no in-service issues reported. So my first impression upon walking up to the fuel truck in San Carlos is that 100R has a unique and distinct smell that is noticeable from a distance. So you certainly will know if you have a leak in an aircraft. And as noted in this Reddit thread, one user mentioned that it smells like Sharpies mixed with acetone. I let a few friends smell the fuel, and they tended to agree that the smell was not obnoxious, and it does tend to smell like Sharpie. I wanted to quickly point out a question that was raised by Scott Perdue of Flywire to Chris DeCostos with Fuels a couple months ago. And it was purported that the ETBE fuel would have a sedative effect if a leak occurred in the cockpit. Chris provided a response from his chemist that ETBE is a different chemical property than ether in medicine, and I've posted the link in the description below. San Carlos Flight Center has reported no incidents of anyone being sedated by the fuel. In early September, Swift announced that they had received their ASTM production specification, which will unlock many opportunities for them to begin distributing their fuel. And as Eagle points out, just about every fuel available for purchase today, even outside aviation, has an ASTM specification. Swift conveyed to me that one of the things in the ASTM spec is the color of the fuel. And the side tube on the fuel truck does give off the green tint that the fuel's been approved given its ASTM specification. Here's a couple photos of 100 low lead and 100R side by side in different lighting conditions outdoors to distinguish the difference between the green and blue colors. And lastly, the fuel does seem to evaporate quite quickly when it's laid out on the surface. And there's no shortage of discussion on the internet right now regarding whether ETB fuels can replace the octane requirements of 100 low lead. I'm going to leave that issue aside right now, and for the rest of this episode, focus on materials compatibility testing. For the materials compatibility test plan, I had two primary goals. First was to apply the same standards, i.e. tests that I applied to G100UL on 100R. And where I was not applying the same materials or standards and testing new ones, I also decided to compare or back compare with 100 low lead, UL94, and G100UL as necessary to have an even playing field. I tested easy turn lubricant, aka fuel lube, nitrile O-rings, fluorosilicone O-rings, Viton O-rings, fuel strainer bowl, cork nitrile style gaskets from a Cessna, Mil 6000 hose, painted surfaces which included random panels, the same inspection plates off my Cessna 182 that have jet glow Matterhorn white, and the same Citabria inspection panels, which were a DuPont Centauri acrylic enamel. In addition, the newest test was I dug into fabric surfaces and paint, where I think you'll find the results were quite interesting. Easy turn lubricant testing is relatively simple, by applying a strip of the lubricant and then submerging it in fuel and watching the results. And for reference, this image is from testing I performed earlier this year, where G100UL turned easy turn lubricant into mush, while 100 low lead had little to no effect on it at all. The MIL standard basically says the grease should not disintegrate or dissolve, and there should be no separation of oil or granular particles. And here's the results of 4 days of testing with easy turn lubricant. I think the results speak for themselves. 100 low lead, UL94, and 100R had little to no effect, if any, on the easy turn lubricant, whereas G100UL turned it into mush. The easy turn lubricant, subjected to 100R, remained as tacky as when it came out of the tube. So for this test, I don't foresee any issues utilizing 100R in conjunction with easy turn lubricant. Next up for testing was to look at several chemistries of O-rings in 100R and compare it to other fuels. This includes nitrile O-rings, fluorosilicone O-rings, Viton O-rings, and I even did a spot test when I was out of town in another part of the country looking at non-California, maybe high aromatic 100 low lead with nitrile O-rings. There's been a suggestion that there's high aromatic content 100 low lead prevalent in several parts of the country. Well, I was in the South, in Kentucky to be specific, for some flying this summer, and I tested nitrile O-rings over a 2-day span with a local 100 low lead fuel sample. I wasn't able to get the refinery details, but I was told the fuel came from a rail car in Mississippi. All my subjective smell tests said the fuel seemed to have more solvent in it. The swelling results were no different than that I've seen with California 100 low lead. I performed a variety of tests with O-rings in 100R, and I compared it to both 100 low lead, UL94, and G100 UL for nitrile, Viton, and fluorosilicone O-rings. And I've done my best to summarize the O-ring data here in some slides with plots. But simply put, I didn't see any significant swelling with 100R. If anything, fluorosilicone had the most swell out of any of them. These tests were performed over about a 2-week span, and at this point in time I don't have anything that stands out as pointing to be an issue, but I'm going to continue to soak these O-rings over time, and I'll report back if I find anything notable. In a previous video, I did a spot check of MIL 6000 hose with both 100 low lead and G100 UL, and within 24 hours the hose swelled pretty significantly in G100 UL. And so I did a quick spot check of the MIL 6000 hose in 100R. And after 24 hours, the swelling results were minimal, if any, both externally and internally on the hose. I've started a longer-term test to further investigate the effects of 100R on these hoses. For the cork nitrile-style gaskets, of which this is an aftermarket replacement, I saw very little swelling at all, basically less than 5% dimensionally. I have a longer-term soak test underway to determine if there's any deterioration in the material over time. Cork gaskets are used in many places in the fuel system of aircraft. One is between fuel bladders and the fuel cap filler net connection on wings. There are likely variants of these gaskets with different materials and binders to hold the cork and nitrile together. I believe that some of the aircraft I've looked at previously have had these gaskets compromised with the introduction of a new fuel, and I intend to perform more testing with these gaskets as time goes on. The next step was to see how 100R interacts with paint systems on aircraft. I had picked up some extra inspection patch covers for my Cessna 182 to replace the ones I had previously stolen for paint testing, and decided to test these before I stripped them and painted them. These are an unknown paint type and primer, and the 6-day exposure was given to 4 different fuels: 100 low lead, UL94, 100R, and G100 UL. I regularly applied about 1 ounce to each container until it evaporated, and then repeated that process over the 6 days. After the 6th day, I quit applying fuel to the containers and then set aside the samples. Here's the results after 16 days when I finally wiped off the residue from the panels. As you can see, 100 low lead, 100R, and UL94, if anything, might have had a slight staining, but that cleaned off nicely later. However, G100 UL seemed to attack the paint violently. And by adding denatured alcohol to the paper towel, I was able to remove nearly all of the dye that had penetrated into the pores of these old panels. Next up was to see how Jet Glow Matterhorn White fares against 100R in an 11-day exposure test. Jet Glow was really unaffected by 100 low lead, however it struggled with G100 UL. And since I had some freshly stripped panels now lying around from test 1, I prepped those and painted them to replace the ones I was going to steal from my Cessna 182. The panels you see me removing here were painted in 2005 with Jet Glow Matterhorn White, and are now being set up for the next test where I stage 100 low lead versus 100R with these panels. The panels were cleaned and then subjected to both 100 low lead and 100R individually over an 11-day span. Fuel was added every time it evaporated. At the end of the 11 days of testing, I removed the panels, wiped them clean, and inspected the paint for any damage. And to be honest, I couldn't find any in either 100 low lead or 100R. Jet Glow Matterhorn White is a Sherwin-Williams product and widely used in the aircraft industry. Given my experience with 100R to date, I think it's safe to say that it will have little to any effect on paints in the industry. For my third paint test, I located more of the Citabria panels that started it all in my first video last year. These were painted with an automotive paint called DuPont Centauri, which is an acrylic enamel, and are likely the least resilient paints to fuels that I've tested. Given that I had not yet tested UL94 with paint, I thought this was a good opportunity to see how it fares. I applied UL94, 100R, and G100 UL to each container on an occasional basis as they evaporated. This occurred over a 5-day span. And at the end of the 5-day span, I couldn't notice any paint deterioration on UL94 or 100R panels. By simply taking a paper towel with denatured alcohol any of the slight tint of the fuel was removed from the surface of the paint, and the sheen almost fully restored. You could say that I've saved the best for last. Back in video number 2, I did some testing of a scrap of fabric from the tail surface of an AT6. The results raised many questions about the effects of fuels and what it might have on fabric surfaces. Specifically, I noted that G100UL seemed to have an adverse effect on fabric as compared to 100 low lead. I've referenced the PAFI materials compatibility test plan in previous videos. I feel that it's a comprehensive document that lays out how materials will be tested with new fuels. The central focus is to see how the entire fabric system holds up together, i.e. the fabric, a surface treatment, a cement, and a coating. The last sentence points out that unpainted regions, such as interior surfaces, are likely an entryway of fuel into the fabric system. And once the fabric samples are ready to go, fuels applied over various time frames and observations made. And for this test, I obtained 2 different fabric samples. The first was from a Citabria over 20 years old, which was noted to be Seconite with dope. The second was about a 5-year-old fabric off an experimental Super Cub. It was noted to be Stitz with the single-stage polyurethane paint. Given that these fabric samples were new to me, it wouldn't be fair unless I subjected it to multiple fuels in a full-scale test. First up for fabric testing was the Seconite. This was exposed to 100 low lead, UL94, 100R, and G100UL for a 7-day span. I devised 2 methods for exposing the fabric to the fuel. The first was immersion at the bottom of the bowl, and the second was a vertical piece of fabric to simulate fuel wicking through an edge, hole, or seam of the fabric. This is where things started to get interesting. Most of the fuel stained the fabric from its fuel dye. UL94 curled the fabric slightly, whereas 100 low lead and 100R had minimal apparent effects. However, a milky white substance was left in G100UL's container. On the second day of exposure, I noticed the paint appeared to bubble on the G100UL fabric, and by day 3 it had flattened out and there was the white milky substance. Let's look at 100R's sample. With the exception of a green dye visible on the backside of the fabric, I don't see any curling or adverse effects. And here's the full comparison of all the fabric panels over the 7-day test span. And while this testing is primarily focused on 100R, I couldn't help but notice the milky white substance left behind in the G100UL container. It definitely seems like something in the fabric system has been compromised, and I'm not quite sure what that is yet. It certainly has my attention. With that learning, it was time to move on to fabric test number 2. This again was 5-year-old fabric off an experimental Super Cub, being Stitz system with single-stage polyurethane. I applied the same test methods as previous, where one fabric sample was submerged and the other was allowed to let the fuel wick up. And in general, 100 low lead, UL94, and 100R seemed to have minimal effect on this fabric system, while the one on the right with G100UL did a complete backflip. So let's look at the fabric results individually. Here's 100R of the sample that I allowed fuel to wick up and the one that was submerged. Other than staining, I don't see any issue with the fabric or degradation of any bonding. The same goes for the 100 low lead when applied to the fabric. Other than a little bit of blue staining, the fabric seemed resilient and hadn't changed properties in any sense from what I can tell. The fabric exposed to UL94 also exhibited staining, and since the purple dye in UL94 is slightly darker, it was a little more prominent in the fabric. However, I didn't see any degradation in the fabric itself. The most interesting result was when the fabric was exposed to G100UL. As you can see here, when I first went to remove the fabric that had been submerged in the fuel, the fabric layer came completely separated from the paint and silver layer. And as shown here, the wick test revealed that where the fuel had not yet made its way up the fabric, the silver layer and paint layer remained attached to the fabric. So I reran this test with a bonded fabric layer with reinforcement tape, and the results were the same. However, this time I noted that it seemed to dissolve the fabric cement that was bonding the layers together. And on the wick test, it showed the same results as previous, where it attacked whatever was bonding the silver layer to the fabric, and likely the fabric cement that holds the layers together. It remained taut where the fuel had not yet made contact with the fabric. So like any good engineer, I reran the same test, with all 4 fuels being applied to bonded layers of fabric with reinforcement tape. Here's the time lapse, which observes the respective fuels and fabric over a 2-day span. Here's a still photo after 48 hours exposure to the fuels. I've sped up this video, but to summarize, UL94, 100 low lead, and 100R didn't seem to attack the fabric attachment. I used an X-Acto knife to pry up underneath and was able to pull it back a little, but the fabrics were firmly bonded together. On the other hand, G100UL did as what it did previously and actually separated the layers of fabric and softened the attachment to the paint. And to put this in context, each fabric sample was only exposed to less than 2 ounces of fuel over a 48-hour period in order to achieve these results. Let me quickly summarize my observations, and then I'm going to explain why I think this is an important finding. There was slight staining on most fabric from the fuel's respective dyes. UL94, 100 low lead, and 100R appeared to have minimal, if any, effects noted to the fabric system. G100UL appeared to separate the bonded layers of fabric and remove the paint layer starting at the silver surface. I believe that occasional or prolonged contact of G100UL to some structural fabric systems may cause damage, potentially leading to loss of strength and thus airworthiness concerns. Let me be clear, I'm not advocating that fabric should be immersed in fuel. However, spills and leaks occur. Aircraft with cockpit sight gauges, or anything that develops a form of a leak internally in the fuselage, will need to be caught quickly before possible fabric system damage occurs. 2 personal examples come to mind. The first is a filler cap on top of any fabric-covered wing like my Citabria. I can tell you that no matter how hard I've tried, I still drip fuel coming out of the nozzle at times. And fuel drains, due to the weight of the fuel under gravity, often spray fuel back up when sumped from the lowest point in the fuel system. And since the fabric system is a structural part of many aircraft, I believe that any fuel that causes the loss of tensile strength, adhesion, or cross-linking is an airworthiness concern. Swift appears to be holding close to their chest the actual performance of their fuel. We don't know if it meets, exceeds, or is less than 100 low lead's detonation performance. So the question becomes, what reduction in performance is acceptable if adjustments have to be made to engines? 1%, 5%, 10%? Take, for example, the book performance values in our POH. These are based on a new aircraft with a test pilot under ideal conditions. I've flown the same model twin aircraft with both tired engines and new engines, and you can tell the difference. Was the difference that I encountered comparable to any possible detuning, where we might change the ignition timing 1 or 2 degrees? I don't know. But I'm sure this will be all revealed in due time as Swift gets more approvals and the fuel begins usage in the field. One of the questions has been posed regarding STC'd fuels is approvals for engines that are not listed on the STC's AML. For example, I have an 0470-50, which is known as a P-Ponk or North Point. My engine is not explicitly listed on GAMI's AML, and in asking Swift the same question about my engine, they stated that I would need to go back to the STC holder in order to have their fuel added to the approved fuels under that STC. Otherwise, I'd have to seek a field approval, which is a significant effort. So I've posed these questions to the Eagle Initiative for consideration and further guidance. So, some closing thoughts. In general, the 100R testing was relatively boring, and I didn't uncover anything of concern at this time. 100R evaporates quickly and has a strong but distinct smell. I think the fabric topic needs further investigation, especially with G100UL. The octane questions and final engine STC approvals are the elephant in the room. Lack of details and the resulting internet speculation on this topic is causing quite a stir. STC'd engines like mine that are not on the AML of STC fuels are a concern. Given that I've had about a month experience with 100R, I'm not done testing it just yet. I've initiated some longer term tests and some new materials that I'm going to look at, so I'll report back when I have more information on it. Again, thanks for watching and have a great day. This is Mike the Mechanic from the Amateur Standards Testing Matrix facility, signing off. See you next time.